So I'm going to talk maybe less about algorithms and more about applications, especially when it comes to material science, materials physics, which is basically what my expertise in. I really enjoyed this workshop. In fact, it kind of gave me an idea the first day when there were beautiful images, tomographic images of human brain, which is really fascinating to think about. And I wanted to kind of explain that, in my opinion, and a lot of my work is basically based on the idea of looking at Operando, which basically looking at devices or materials while they're operating. And it kind of goes back to the idea that we want to kind of close this loop and understand how the structure affects the function, and function in turn can affect the structure. It's a little bit like if you think about CAT scan, it's just more of a passive image of the brain. But then functional MRI is similar type of image of the brain, but while it's operating, right, while it's thinking. So this is obviously a perhaps much more important sort of area of research if you're a neuroscientist than just doing sort of more static, passive type of images. You want to understand not only what the structure is, but also what is, how do those neurons and synapses firing while you're thinking about something, right? That's really important to understand in how the brain works. So we have somewhat of an analog in material science. We want to understand how devices operate sort of in real time. So first, actually, for young people, I wanted to say that we do have postdocs in my group. So if you guys if you're interested in what I'm going to say, you should consider going to UC San Diego campus, which is kind of like UCLA campus in terms of the weather, except it's much closer to the ocean. So, and some of you who made a walk to the ocean, you can do this much faster than even from John Mayall's house. And the physics department is somewhere here. I think I kind of identified it properly. This is a little bit of an older photograph. The campus has expanded quite a bit since. Many of you have been here, right? So Hyun-Jun spent her postdoc years, and Ross has visited, and others, I'm sure. If you want to visit us at some point, I'll be happy to host you. All right, so actually just a couple of ideas since I'm doing this commercial about my group, right? So I want to say that today I'm going to talk about this part, which is ionic materials, but we do a lot of work on different materials. We're a little bit schizophrenic in the sense that we do work on magnetic materials that I generally call quantum correlated materials. This is obviously in physics, that's one of the major themes. We also, instead of doing just imaging or slow dynamics, we also been applying XFELs to study ultrafast dynamics. And then on occasion, we do work on some weird offshoots, like for example, biophotonic materials, butterfly wings, literally, which are photonic materials that are made by nature. And these are all studied by various X-ray techniques in my group. This is just a couple of examples. Again, if you're interested in those lines of work, we did a lot of work on XFEL about ultrafast dynamics and things like spin and charge density wave systems. We also did, and still doing a lot of work on X-ray photon correlation spectroscopy, which is another application of coherent techniques to study, typically slow dynamics, but we've been pushing, and other groups have been pushing it towards faster and faster timescales using XFELs, where you can apply the same techniques at sub-picosecond times, perhaps, in the near future. And we also apply other techniques that not necessarily based on coherent diffractive imaging. So today I'm going to talk primarily about this stuff on the right, which are based on CDI, coherent diffractive imaging. But we also use, I learned it from Chris Jacobson, right, many years ago, before I even became the faculty. If you have a lens, you should use it. That's what Chris told me when I was a young postdoc. And so a lot of times we use scanning microscopy, scanning nanodiffraction, for example, to look at other types of defects in the situations where that's more appropriate. Okay, so let me kind of give you a little bit of motivation of why I came to this field of energy science. And I think I don't have to spend too much time on these slides. Everybody knows that the world is very hungry for energy. There is a lot of parts of developing world that wants the same standards of living that Americans enjoy, and obviously that pushes demand for non-renewable energy sources like coal and oil, and of course burning those is not very good for the environment. And even though the renewables, which you can see here kind of with a tiny little green line here, has been increasing, you would think dramatically, but it's still not really quite on the same level as sort of more traditional non-renewable energy sources. And therefore, if we're thinking about transition into more sustainable energy, it includes many different solutions. If you think about energy grid, how do you store the solar, or wind energy during the day, and then you want to use it during the night, you need to figure out some sort of storage solutions for the grid. If we're thinking about applications like electronics, everybody has cell phones in their hands and everybody's on the laptops, right? So you guys know how important battery life to your devices is. And of course, over the last couple of years, we had a lot of big revolution in transportation, where there's more and more electric vehicles emerging. I've seen some electric robots running around in UCLA delivering food. So all of that requires solutions in terms of energy storage. There is an article in Science that was, it's quite old now, it's 5 years ago, written by Barack Obama, which basically summarizes why we need sort of a global solution to move towards clean energy. It has 849 citations if anybody wants to check. So for young people, if you're the president, you can publish in Science and it will be cited. There is a number of parameters that engineers, my friends in engineering departments, really want to consider in terms of what is the best material for the next generation energy storage solution. You can think about it, and these are only just 2 axes. You can think about, for example, sort of specific energy, which is watt-hour, the energy divided by the weight. This is very important for, if you want to carry a phone in your pocket, right? You don't want it to be heavy, but you also want the battery to last all day. Same for your laptop, the same for your battery in your car. And then, of course, there is specific power, which is wattage per kilogram. And this is important for power tools. And again, for the car, you want to accelerate it fast. So the power to weight ratio is also very important. And there are many axes that are not even shown here. So by the way, this is one of the, so of course, I'm going to talk about lithium ion for the most part. I'm going to talk a little bit about sodium ion batteries, which is a new sort of development that we started working on recently. But there's a whole bunch of other systems. So you can, of course, have nickel metal hydrides, supercapacitors, lead acid batteries, and so forth. There are many other considerations from the engineering and industry perspective. You want batteries to be safe, right? You don't want them to explode in your house or in your pocket or on your airplane. You want them to be relatively inexpensive. You want them to last longer. You don't want to replace, and we'll get to that point in a second. You don't want to replace your phone every 3 years just because the battery stops charging. You want them to be made out of easily accessible materials. So lithium is not ideal from that perspective. If every person on the planet wanted to have an electric vehicle, we wouldn't be able to mine enough lithium from all the mines across the world to make it happen very quickly, right? And that's why there is a lot of applications that are looking into other materials like sodium-based, for example. This is just a very simple cartoon picture. So even though all of my engineering friends, they care about all this stuff, I actually care about more fundamental questions as a physicist. So this is a physicist cartoon of what batteries look like, and my engineering friends would probably roll their eyes at this picture, but this is good enough from my perspective. So essentially you have, in a very simple picture, you have a cathode that is usually some sort of open structure, typically an oxide that can host lithium ions, and then you have an anode, which is typically something like a graphite, and when you charge the battery, you can basically shuttle the ions from the cathode to the anode and then back. And of course, electrons go through whatever piece of equipment that you're connecting it to and sort of meet with the ions on the other side, and you repeat this over and over again. I wanted to say something controversial, and I believe it's true. We actually don't really understand how the battery works. And by we, I mean not just myself, but basically nobody. Even people in engineering departments, physics departments who work on batteries, they don't fully understand how the battery works. And when I say this to people, they say, what do you mean? Of course we know how the battery works. We have them everywhere. We know how to make them. We know how to maybe even improve them. But we don't fully understand the fundamentals of what is going on inside of the battery. And that's basically, I'll show you a couple of examples of where even the people who have been working in energy storage for decades don't have very simple answers to what is actually happening inside. And I just wanted to say that, so I'm going to focus on the cathode side, which is basically this, typically these are oxides. Oxides are great because there is a whole large family of them, so you can easily come up with new materials by simply substituting different elements. Just to give you some ideas, these are sort of commercial cathode materials that different companies have been using, and they're all basically open perovskite structures which allows the large ions like lithium to go in and intercalate it between different planes. And there is different 1D, 2D, 3D type structures that people can make. And for various reasons, different companies try to go for one material or the other. But again, from zoomed out version, they're all basically similar type of family, same family of materials. So this is I'm sorry, somehow it doesn't show. Hold on, let me see if somehow this got erased. Let me go back for a second. So I apologize for this, but the question that I wanted to ask here, and maybe this is even better, can we actually see inside of the materials during the operation? Somehow this image doesn't show, but this is even more mysterious. What is actually going on inside of the materials while the device is operating? And the second question that I wanted to pose here is, can we control defects and disorder to tune specific functionality? And in physics community, disorder is kind of a dirty word. It means that you've made a mistake when you're making the material and now something is bad, right? The sample made a mistake. Now it has a lot of defects and it's bad. But engineers, material science will tell you that a lot of times you actually want defects and disorder, right? And if you think about even the older profession of making things out of the metal, right? The blacksmiths, they know how to incorporate defects to make materials to what they want to be, right? To make them stronger, to shape them in a certain way. And in the same way, we can apply these principles to nanoscale sort of manufacturing nowadays to fine-tune some of the density of defects in order to get what we want. All right, so what is inside of your battery? So if you take any battery, it could be from your phone, but typically we work with sort of smaller dimensions like this coin cell, and literally just peel off the back of the coin cell, and you look inside, and if you zoom in under the microscope, let's say the SAM image, it doesn't look like a very nice type of material. It's not like in physics we like to grow perfect MB grown films which have no defects and everything is smooth and well ordered, large crystals that again everything is perfect. They look basically like little pieces of grain of sand that we saw yesterday at the beach and kind of smooshed together. The dimensions of these particles are typically on the order of sub-micron, and that's by design. You don't want particles that are too large because that takes a long time for the ions to diffuse in and out of them, so that slows down operation and charging rates. You don't want the particles to be too small because then the surface to volume ratio, you can think of surface as kind of like a defect, large defect, reduces some of the functionality. So there is sort of a happy medium somewhere in the range of between an order of hundreds of nanometers where these particles function in the best optimal way. And these are usually powders. So this is basically the anode material. This is the powders which are then separated from the anode by electrolyte and a separator. And so what we can do with X-rays, and this is essentially my expertise, we can come in with X-rays and we can pick out one of those grains of single crystal grains. And because we have a well-collimated monochromatic beam, similar to probably what you've already heard from Ian and others, we can basically satisfy Bragg condition only for one of these particles and not all of the particles, and we can study a specific particle. That's basically the idea what I wanted to show you. Yes, Chris?
How many of them are polycrystalline particles versus separate nanocrystals? In other words, do you have kind of aggregation of different nanocrystals?
Yeah, the aggregations of nanocrystals, and sometimes they're kind of like there's a clump here and a clump there, and they do have some loose connections between them because you still want to have electric connectivity. If you disconnect a clump of them, they become, and we've seen that by the way in our experiments, they just become basically inactive because you still in a functioning device you want all of them to participate as a single electrode, right? So let me kind of give you a couple of the easy experiments, and this is actually done at Ross's beamline, and Ross probably hates this experiment. The idea here is that we're actually coming in and illuminating large beam, unfocused beam that illuminates not just a single particle that satisfies Bragg conditions, but it's done in such a way that multiple particles satisfy the Bragg condition. And so each of these particles on the detector gives you essentially a little Bragg peak. And this is the powder ring, so you can think about this as a Q vector, so it's effectively 2 pi over the lattice spacing in a crystal. And so each one of them is a specific particle, right? And now I'm going to play a video of us. We're doing this to the battery while it's operating, right? So we're going to discharge and charge it. So let me show you what happens. So right now we're removing the ions from the cathode, right? So, and as a result, the lattice constant shrinks. And you can see it moving, the Bragg peaks, all of them kind of moving, not at the same time, right? There is a little bit of a lag. They move into larger Qs, smaller dimensions, and then we're reversing the process by putting the ions back in. There is a phase transition. That's why you see a jump from one Q vector to another. So all of you who think in reciprocal space will understand what's going on. And the cool thing here is that, we can do this. We can watch it and kind of try to analyze it in many different ways. I'll play it again. The other thing is you can see that there is a little bit of a history. Since the process working one way is not the same as it's working the other way. There is this phase transition let me just tell you that the phase transition is what material scientists like to avoid, because this is basically could create, it's kind of a catastrophic thing for if you're a particle, right? You have to undergo a sudden phase transition, which could create cracks, it creates a lot of strain. It's one of the reasons why you should not discharge, if you own some of those electric vehicles, you should not discharge your battery completely. And a lot of times they artificially put a limit, so you don't go through the phase transition, which usually happens on one side of the charge-discharge curve. But the interesting thing is that also by following multiple particles, we can kind of understand that not all of them go through this process exactly the same time, even though they're in equilibrium with each other, which tells you already something about that the presence of defects or the size differences are important in the system, right? It's not happening uniformly, so to speak. Okay, so there's many ways that you can analyze it because you can correlate it now to so the idea here, let me actually kind of jump through this. I already talked about this. So this is kind of like the dimension. I'm playing this again, but let me kind of jump to this a little bit faster. So we can plot the diagram for what happens in the charge-discharge state, and we can see the hysteresis, and we can do this for a large ensemble of the particles, but because we have access to a finite discrete number of particles, we can kind of analyze it particle by particle and try to see what is the distribution in terms of how each particle goes through phase transition and back individually as well as an ensemble, right? So that's actually, from the engineer's perspective, this is like the greatest thing ever. We didn't even get to the coherent diffractive imaging, right? Because they can kind of try to understand it not in a completely global way, but doing a little bit of a discrete sort of powder type analysis. And that already tells them a lot of information. There is hysteresis that is, again, I would argue that none of my colleagues and even I don't fully understand the source of hysteresis, but obviously it means that anytime you have a hysteresis in a system, that means that your battery actually knows whether it's being charged or discharged at the same voltage state, right, the same charge state, which means that it has a little bit of memory, right? And that means that there is probably some sort of defects that guide that memory. How else would you basically violate the thermodynamic equilibrium if you didn't have some sort of defects guiding it? But we wanted to kind of go beyond that. And the question is, can we zoom in into one of those powder diffraction peaks and try to understand what happens at the individual particle level? And so this is essentially the core of my talk. And I can skip, for this audience, hopefully I can skip this, right, this slide. We've heard a lot about this. But the idea here is that we use Bragg coherent diffractive imaging that many people here understand very well. The idea is that we measure three-dimensional reciprocal space speckle basically around the Bragg peak, and then we can invert it. And by inverting it, by solving the phase problem, we can get a real space image of what the particle looks like in 3 dimensions. And this is really cool. And the important step here is that in addition to getting the shape of the particle, which is what you would get in a forward scattering transmission geometry, you can also get, and I'll explain this in the next slide, as something called the displacement field, which encodes not just the density of the particle, but also essentially strain or defects that occur inside of the particle as well. And that's an important part of this process. So just kind of an illustration, this is kind of a movie of rocking through one of these Bragg peaks. That's how we collect three-dimensional information, by simply tuning to one of the crystals and then rocking it around. And then by solving for phases, for the missing phases, we get the shape of the particle and the internal structure. And so this has been known, and again, Ian and Ross have this wonderful paper in Nature Materials that kind of explains all of that, and a lot of people, and Ivan, who's going to talk next, is one of the people who worked on this in early days of this, which basically explain the whole process and how getting the imaginary part of the complex valued density function is actually giving you a lot of information about the strain. If you're not really the kind of a material scientist, let me give you a very brief explanation. If you have a perfect crystals where all the atoms are exactly where they're supposed to be in the exactly periodic location, then if you tune to the Bragg peak, all the atoms will scatter exactly in phase together, right? They're thinning in phase and scattering all the rays to the detector without creating any phase differences. But if you start moving the atoms, if you start displacing them from their periodic locations, then these guys will start scattering slightly out of phase from their neighbors, and the amount by how much this scatter is going to be related to the projection of this displacement field, where the atoms are versus what they should be, projected on the scattering direction, right? That's basically how much out of phase they are from the planes of their neighbors. And this is the way we encode, effectively, this displacement field is encoded in a complex valued density function. Okay, so why is this important? Because as I showed you in that movie that I played, when you intercalate lithium ions, the lattice spacing changes, right? And that basically does it creates the displacement field that we've talked about before. And so if you do this for a partially charged particle, for example, you will see the regions that are lithium rich and lithium poor, just simply looking at what is the lattice constant at different parts of the particle. So this is one of those particles that we would just study at some intermediate state of charge. So let's say you're looking at half-charged state in your battery, and so the particle in this case has bright red regions that are lithium rich and bright blue regions that are lithium poor. And because we have three-dimensional information, we can also do all kinds of scans and try to visualize it in 3 dimensions. So this is just it's a core cut from this 3-dimensional slice that we're studying. Another way to do this, and this is maybe a slightly different particle, but the idea is that you can also slide it like a potato, right? And again, you see that the regions of lithium poor and lithium rich are kind of separated into stripy type pattern. And when I first saw this, I was going around asking people who study batteries, like, what do you expect in a half-charged, state? Where are the lithium ions are going to sit? And most people who know anything about thermodynamics would say, of course, it's going to be randomly distributed. Lithium is going to be kind of like people sitting here in this audience. They're going to be randomly occupying the spots in the seats, and half of the seats are going to be empty, half of them are going to be filled with people, but it's going to be randomly distributed. Because why? Because entropy, right? If I sprayed perfume in this room, the molecules of that perfume would randomly occupy all the points here, right? It would be very unusual to see it clump up in sort of stripy type of behavior. Some people who study batteries for a living would tell me, well, maybe it's more like a theater full of people who are exiting, and half of them exited, so the middle of the theater is going to be empty, and everybody's going to be clumped up to the exits. And that's not what happened here either. So none of those two scenarios that I've heard from anybody who studies battery for a living is correct. In fact, we have this sort of stripy behavior where lithium-rich regions and lithium-poor regions are sort of clumped up in a stripy type arrangement. And it turns out that some people didn't understand this, and they wrote this paper where basically, as with any thermodynamic system, you have to balance, and entropy has to be balanced by something else. In this case, it's balanced by enthalpy. And enthalpy has to do with the fact that you create in strain fields anytime you put a lithium in. And there is a cost associated with creating boundary between large d-spacing and small d-spacing. And because you have to pay the price for the domain wall boundary, at some point there is a balance between entropy on one hand and enthalpy on the other hand, enthalpy of mixing on the other hand, that leads to the formation of the stripes. And this is basically the reason why any stripes form in any physical system. And it's kind of ubiquitous in everything from soft matter to plasma to lots of other, to superconductors and so forth. The interesting thing is that when you consider the thermodynamic implications of this, the balance here is essentially between the temperature, which drives the entropy, and the cost of having that enthalpy, the cost of having the domain wall between lithium poor and lithium rich regions, which allows us to do something really cool here. It allows us, first of all, understand what that energy cost is for the domain wall. Essentially, it's the surface energy of having a domain that has lithium poor, lithium rich regions. And if you calculate it from our analysis of 3-dimensional representation, it happens to be about 100 millijoules per meter squared, which is kind of like 100 dynes per centimeter squared. It's basically the same as roughly a surface tension of water, which is actually a pretty high number if you think about it. The other thing that is really cool is that we can actually, because we measured the elastic property of the entire particle, we know what the distortion of the particle is in 3D for every point of charge and discharge. We effectively have a total elastic energy of the particle as it goes through this charge-discharge process. And by integrating over the full 3 dimensions, we can get elastic energy shown here as we're charging and discharging. You can see that there is a barrier that it tries to overcome, right? And that's the origin of the hysteresis that we still don't fully understand what we measured at with femtojoule resolution, if I may say, because we measured the elastic fields with such high precision for a very small particle. And we can see that the barrier is displaced on charge and discharge points, and it's also a very different height. And again, you can argue now about what is the origin of those barriers, but we've measured that in a very precise way by taking the particle through multiple charge and discharge cycles. Okay, so this is kind of one cool experiment that you can do. You can basically study what is happening in the energetics of a single particle that undergoes all these transformations with femtojoule resolution and looking at all these barriers and so on. But there is an even cooler thing that I'm really find fascinating, is that in some of these particles you can form dislocations, and this is just, again, those of you who haven't taken material science or haven't taken it in a while, you can think about edge dislocation, for example, as simply taking a crystal, which is perfectly well ordered, and then inserting a half plane of atoms here, which basically creates a topological defect, because if you're a little guy walking inside of the crystal and counting your steps and trying to come back to the same point, anytime you go around the core of the dislocation, you'll be displaced by one unit cell, right? If you make 4 steps, 4 steps, 4 steps, 4 steps, you're not going to be back to where you started. You're going to be offset. So this is an edge dislocation. There are other examples of like screw dislocations. The reason why they're important is that in a lot of the oxides, these edge dislocations can provide a very fast way for the ions to diffuse through. And it's not just for energy storage materials, but basically you can take STO and look at oxygen diffusion. And the oxygen diffusion, once you create enough dislocations, will be very fast this way, will be actually worse off in other direction, right? It's kind of like a little super highway. Yesterday, driving on 405, I was actually thinking about that this is a fast way, but then everybody who lives around the highway probably is impeded by the presence of the highway. So it's kind of good and bad at the same time. If you want to speed up the charge process, you want to have some dislocations, but if you put too many of them, it kind of constrains the overall diffusion through the 3 dimensions. So why is this important? Well, so again, people have been arguing about the importance of these dislocations, and the cool thing is that we can actually see them, of course, with our X-ray coherent diffractive imaging. Why? Because we're measuring the phase, and if you think about mathematically what that topological defect of inserting half sheet of atoms inside of your crystal, in a 2-dimensional cross-section, it means that when you go around one of those points, you'll accumulate a phase wrap of 2 pi, effectively, because you accumulated an additional 1 unit cell displacement. And you will have one phase shift of, let's say, plus 2 pi going around this way, around one core of dislocation. And then if there is a sort of the opposite sign of dislocation, so if you created 2 pair of dislocations with opposite Burger's vectors, going around the second one, you're going to create phase of wrap of minus 2 pi in the opposite direction. And that's exactly what we find here. So if you look at it, this is a zoomed in version of what I'm showing here. But this is what our measurements show, that there is 2 pairs of dislocations that are basically created. It's as if somebody took a sheet of atoms and tore it in half. And now you have a pair of dislocations of opposite signs. If you can bring them back together, they will annihilate again and will disappear. But there is a positive and negative sign dislocation, if you will, now created in this crystal. And the cool thing is that actually these dislocations, they usually don't exist in a pristine material, but you can induce them if you essentially abuse the material by charging it fast or exposing it to multiple cycles. You can create more of them. The other cool thing, and we can prove, by the way, that this is a dislocation, pair of dislocation, not only because it shows up and as a dislocation in terms of the phase factor, but there is a really cool way that we can prove that it's not just any dislocation, but it's really an edge dislocation, another screw dislocation, is because we have a strain distribution around this point. And if we measure the strain distribution around this point, it's not uniform, it's not constant, which you would expect for screw dislocation. It has some variation, and it fits exactly onto what the standard model for material science model would predict as a result of having this edge dislocation. And the only fitting parameter here is the Poisson ratio and the unit cell, which we already know, of course, because that's where the Bragg peak is found. So effectively, it's also a measure of elastic properties of the crystal around that dislocation. There is a weird thing that happened there that I'll admit that I don't fully understand, which is at some points this parameter becomes negative, which means that it means that when you push on something instead of compressing it, it expands. There are predictions about this kind of materials, but it's too exotic for me to really speculate about exactly the origin of that. And it only exists in certain parts of charge-discharge cycle. And again, just to illustrate, this is an example of kind of edge of screw dislocation. Screw dislocation would be sort of like a parking lot structure where if you drive around, you kind of go in the spiral, right? It's one of those situations where you go around and then you end up at one floor down or one floor up. Whereas in this case, we're talking about edge dislocation, which is an additional row of atoms. So we basically identified it as this one, as the left example, which is the edge, instead of the right example, which is the screw dislocation. And again, I mentioned that we can measure Burger's vector, which is already known. That's the unit cell size. And also Poisson ratio that goes negative in some parts of the charge-discharge, which I don't think anybody fully understands. We try to ask many people to calculate these properties, and people claim that yes, of course, we could make it so in our models, but I don't think anybody could have predicted it or really explained it away. And this is just to show that we can model this stuff, right? So we can create sort of artificial dislocations, see what the phase reps would look like, and it looks basically more or less exactly what we saw in our reconstructions. So another couple of cool things is that, again, is really interesting, is that when you charge or discharge, these dislocations actually can move. Usually when you think about defects, they're kind of static, right? Unless you heat it up to the point where, close to melting points, they will start moving. But in this case, these defects are static by themselves if you don't do anything to the device. But when you start passing the currents themselves, because they involve motion of the ions and involve redistribution of strains, they can move these dislocation lines around through the crystal. And we can visualize it as it happens basically in real time as we're going through the cycles of charge and discharge. And that's, to me, is both. It's interesting from the perspective that we can control them by means other than temperature, right? We can perhaps even drive them with currents in specific directions in these materials if we wanted to either drive them away or move them in a specific controlled way. The other thing that I think is also interesting here is that when we go through that phase transition that I told you that you should always avoid if you have a battery that you don't want to die too early, that phase transition actually originates kind of roughly at where the dislocation core lies. So the dislocation serves as a nucleation center for the structural phase transition, which is, again, exactly what you would expect. You need some sort of nucleation point. But it could also mediate, to some extent, this cracking that is a large problem in materials world, because by nucleating it, you're reducing stresses that would have built up if you didn't have a nucleation point, and you would have to do it, in a more sort of dramatic way, I guess. Let me switch gears a little bit and tell you a little bit about, so this is the material that I talked to you about previously. It's kind of more standard material that you can find in basically all the devices that you are using today. But in recent years, there was sort of this new kid on the block, and this is a really exciting new material. They're called lithium-rich layered oxide materials. They're not in applications yet, but the exciting thing about these materials is that they have about 50% excess capacity, which means that they have 50% more energy storage per weight than any material that is used in Tesla today, any of the cars. That means that if you could commercialize these types of materials, they're still based on layer oxides, you could go 50% further on the same charge, right? There is a problem with these materials. Well, one problem is that, so by the way, the industry is actually looking at those materials, but there is a big problem with them is that there is a degradation of these materials. You cannot cycle them as often as you would like. I'll tell you two major challenges real quick, and then I'll tell you the third one that I should have mentioned up front. So basically, two major challenges are kind of related. You can think of them as one major challenge, is that if you cycle it, let's say 50 or 60, 100 times, there is a big degradation in terms of the capacity. It's a significant drop. And also in terms of the voltage that the cell produces. This is something, obviously, that is not desirable. You don't want to buy a car and have to replace the battery every time, every 50 days. Or a laptop that's, a cell phone that doesn't last that long. So you would probably not, it's not ready for the prime time. The other weird thing that I forgot to mention here is that when theorists, right, who use DFT try to model this material, they cannot come up with the argument of where this 50% extra capacity comes from. In fact, all of the calculations can get you maybe 20% extra capacity, but the experimental data basically is much better than what theorists with the best tools that they have can predict. To me, it's a little bit mind-blowing because it's always the reverse, right? The theorists always tell you how something is going to be great, and then you test it and it's much worse. In this case, it's actually much better than what theorists can predict, and they cannot figure out exactly why that is, which tells you a little bit of the level of complexity involved here. I mean, there is always, some ways to maybe, fudge the numbers, but to me, it's a little bit, it's quite remarkable. So we wanted to understand a little bit better about what is actually responsible for this capacity fade. Can we actually fix it somehow? And this is the work. And again, we've done basically the same process that I described to you previously. We were looking at coherent diffractive imaging, and we're trying to cycle it multiple times and trying to understand what is actually happening in this material after you cycle it many times. And people who kind of train to see things in reciprocal space by looking at it, and this is basically kind of increasing the voltage, by looking at the diffraction patterns, some of you may actually kind of figure out that as you're charging it, it becomes more and more defective, so to speak. There is more complexity in the diffraction patterns as you increase the voltage. But let me kind of show you what the reconstruction show you, because my postdocs and students claim that they can see it, and I can maybe kind of see it if I squint my eyes. But if you look at the pristine material as it made, it has no defects. This is one particle that I'm scanning it through back and forth using the CDI reconstruction magic, and you basically see that there's a little bit of strain, but there is no defects, and you would see defects as those pinch points with the color all of a sudden wraps by factors of 2 pi. But then as you go to higher voltages, so again on the left, at 4.3 volts, all of a sudden as you charged it by only increasing the voltage by less than 10%, immediately see a pair of dislocations appear here. And again, you can see them as pinch points here and there. And this is a three-dimensional sort of slices through three-dimensional object. And you can see this two-dimensional slices through 3D object having those pinch points, and you can follow those lines, and they basically look like this. So by applying the voltage, you create these defects. And if you increase the voltage even a little bit more, then you create more defects. And the worst part is that at some point, it becomes so defective you can't even reconstruct it. It becomes too disordered to really follow the evolution of those dislocations. But you can see how from 4.0 to 4.3, you have a pair of dislocations. By 4.4, another 100 millivolts, you created a whole bunch of network of dislocations here. And so we can kind of analyze it, and essentially it's as I told you before, it's equivalent of inserting an extra sort of half plane of atoms in a specific direction in these materials. And again, like this is another way to visualize it by either looking at the phases or looking at the derivatives, which is kind of the strain, right, of the displacement field. And again, now you can see these pinch points as sort of these regions here that give you this phase wrap, this kind of butterfly type patterns of strain around them. And there is more of them as you go to the high voltage. So we believe, right, correlation is not causation, but we know that this material deteriorates as we introduce in more and more of these defects. And so how do we really prove that that's not just some sort of spurious correlation, right? That it has nothing to do with the performance. Is it that in this case, dislocations are really bad for the performance of this material? And one way to answer it is to say, well, if it's really the defects that cause this deterioration, then maybe by annealing this material and removing all those defects, you can gain back some of this voltage, right? The functionality, which is what you ultimately are after. And that's exactly what we found. So essentially by cycling it 40 times, we see the degradation and we see the formation of these defects. But then as soon as you treat it, and you can treat it 2 ways. You can either apply pressure, or you can heat it up, or you can do both at the same time. It basically recovers the voltage. So it jumps from 3.3 to roughly 3.6, almost back to the normal conditions. And we even without doing the full sort of CDI, we can just simply look at the one of these. It's kind of like a half order peak, and as soon as you start inserting these half planes, that peak disappears because you introduce enough disorder that there is basically the Bragg peak disappears. But after the recovery, it's not quite fully there, but you recover most of it, I would argue. And so it shows you that there is a structure-function relationship here. By annealing this material, you can recover most of the original properties, and you can reset it back. Obviously, that's not a good solution. If you want to have, you don't want to return your battery for annealing. You don't want to bake your battery every 40 cycles just to get back the recovery. But we're hoping that by clever material design, we can prevent those dislocations from forming. So maybe some clever doping or some other processing technique that can prevent those defects from formation. But the basic summary of here is that, and this, by the way, this also has been confirmed with first principle calculations, which as experimentalist, sometimes I put a little bit of grain of salt because depending on the parameters, you can kind of prove almost anything you want. But basically, the first principle showed that the dislocations do, in fact, in these materials correlate with voltage fade. But more importantly, it's confirmed by the fact that the high temperature treatment or high pressure treatment, which is something that my colleague Shirley Mann is now patented because she doesn't tell people exactly her secret recipe for baking these materials back to normal. But you can basically recover the full functionality, and we're trying to. They're trying to work now on trying to come up with the ways to preempt this from happening to begin with, right? So that's basically another story that I wanted to tell you, and then I have the third story. If I have a little bit of time, I'm kind of running out of time, but I'll just use like 10 seconds. This is a story that is not even complete yet, but in the past couple of years, we started working on slightly different materials, which are solid-state electrolyte batteries. These are better from a number of perspectives. There is no flammable liquid electrolyte. So when you hear about stories about planes exploding, because somebody has a phone and it goes on fire, you don't want that to happen. You don't want it to happen in your house. The second sort of advantage to these materials is that we're looking at sodium-based instead of lithium-based, so different ions. Lithium is good because it's very light, even though energy density could be actually still very high for sodium. But sodium also has the advantage that it's cheaper, right? You literally have oceans full of sodium, outside of UCLA and UCSD, and so you don't have to mine it as much. And if you're looking for solutions where something sits in your house and collects energy during the day when the sun is shining, and then you watch TV later on, you don't care if it's lithium or sodium. It just sits in your garage, and you don't care how much it weighs. But there are issues with these approaches because there is poor interfacial stability, and that's kind of a chemistry problem that I don't want to talk too much about because I don't fully understand it. And also there is a lower ionic conductivity, which means that the charging and discharging takes forever. And so we're trying to address the more of a second problem, even though at the same time our colleagues are trying to also address the interfacial stability thing. And so these materials actually have been shown to be very robust, and you can take them through 500 cycles, for example, and still have unlike the previous ones that I showed you before, you can recover them. So these are basically this work by my colleagues shows that you can cycle them and you get very good durability. And the interesting thing here is that you can take these materials, and the host material that is sodium yttrium chloride has very poor electric conductivity. But if you dope it with a little bit of zirconium that replaces the yttrium, then you can actually boost the conductivity by something like 2.5 orders of magnitude, which is fantastic because that's exactly what you want. You want your ions to be able to flow back and forth much more freely. Again, I would tell you that nobody understands exactly why that is, because the calculations, DFT doesn't really show that in their modeling. So we try to set it out to see if there is anything in terms of anything else that happens in these materials when you dope it. And again, these are somewhat preliminary results, but when you do the reconstructions without assuming anything, what you end up with a whole bunch of domains that basically show pi phase shift inside of them. So it almost looks like a antiphase boundary domains, which basically is equivalent to shifting the colors here by a factor by a phase of pi. So if you kind of look at the colors, you see these two colors kind of present, and they're offset by essentially half of the unit cell. And we can see this in a little bit more detail as you dope more zirconium here. You get smaller and smaller domains of this antiphase boundaries. And then we try to kind of correlate it and see if the density, and it's a little bit difficult to compare, but we try to correlate the number of those defects of these antiphase domain boundaries as a function of doping. And you see that basically for 0% for the pristine material, it's relatively small, but then for larger concentration, it goes up to much larger defect density or boundary defect density. And it's somewhat, again, correlation is not causation, but it kind of follows the same type of trajectory. Whereas you start doping, you have more defects. And now, people that we on the modeling side have redone some of their calculation. They show that if you have some of these domain walls, and if you assume that they change the angle of the octahedra of this perovskites, that could actually, near the boundary, due to some sort of distortions, that could actually affect the conductivity of the ions. So it's somewhat preliminary. We're still trying to get more data, and obviously it's these are relatively fresh measurements. But the hope is that if we can show that these defects somehow are responsible for the high conductivity, then maybe we can try to think about how to stabilize them in a way that, in some other ways, right? Instead of, it may have actually nothing to do with doping. It just has to do with some octahedral distortions. All right, so this is the end of my presentation. So I wanted to thank a lot of people. These are sort of members of my group, but Andre Zinger started a lot of these projects. Now he's a faculty at Cornell. Shirley Mann is my collaborator on the energy side. We actually have this picture of the sort of original group taken several years ago now. But Andre, who was a postdoc, is now at Cornell, a faculty member. Andrew Ubestad, who was a student in my group, he's now at Tesla, making more money than all of us here. And Shirley actually just left UCSD, and she works at Argonne University of Chicago, but we still collaborate on a lot of projects. So I'm the only one in this picture who's still actually staying at UCSD. So anyway, so I wanted to end this, and if any of the young people want to have a postdoc position, please reach out to me. We do a lot of obviously applied work or not applied work, depending on how you look at it. It's very fundamental from the engineering side, but very applied from the physics side. And I'll stop here and ask if there is any questions.